So previously we used Euler's identity to obtain these two identities for cos and sine. So we're expressing cos and sine in terms of the exponential of an imaginary angle. So e to the I times theta and e to the minus I times theta, using those to obtain expressions for cos and sine. And these are incredibly useful identities. So in fact, it's a sort of standard procedure to use these to prove other trigonometric identities. So that's what I'd like to do today, is give you a couple of examples of how you would do this. Now this is an absolutely fundamental technique, and it's one that students often neglect. I mean, there'll often be a question like, prove such and such is equal to such and such, and the first thing you'll typically want to do is make these substitutions, and then things become a lot easier. You can just expand the algebra, play around with it, and it all comes out. So as I say, students often forget this. I'm not sure why, but I'll give you some examples of how that's done. So what I'd like to do is start with some examples. So we've got sine squared theta is equal to a half 1 minus cos 2 theta. Okay, so what you've got to do is prove this using exponential form of sine and cos. Okay, so the exponential form of sine and cos is precisely these two relations here. Okay, so how do we do that? Well, we've got to prove something equals something else. So the standard way to do that is start with the left-hand side and rearrange it until we get something that looks like the right-hand side. Or we could try playing around with the left-hand side and playing around with the right-hand side separately and find that they're equal to some common thing. But what we don't do is write down this. We don't assume this. So we've got to prove this. So this is going to be the last thing we come out with. So let's start by writing down the left-hand side. So the left-hand side is equal to sine squared theta. Okay, so what's sine squared theta? Sine of theta squared, and this is sine of theta. So this is just equal to e to the I theta minus e to the minus I theta all over 2i squared. Okay, and a standard mistake people make at this juncture is they forget that sine has an I in the denominator. So don't forget that little I at the bottom there. Okay, so we can expand this out, expand out the numerator, expand out the denominator. So multiplying out the top, well, let's do the bottom first. The bottom's easier. So 2i all squared, well, 2 squared is 4, I squared, what's I squared? It's the whole point of I squared is minus 1, so we get minus 4 on the bottom, and on the top we just square the top, so that's going to come out at e to the I theta squared plus twice the cross terms, e to the I theta, e to minus the minus I theta plus e to the minus I theta squared. Okay, so just expanding this out. So something to a power squared is just the same as something to the twice that power. So just using the power rules here, we get e to the 2I theta plus, okay, multiplying e to the I theta by e to the minus I theta. Rules of indices is we just add the two indices here, so that gives us 0, so that's plus 2 e to the 0 plus e to the minus 2I theta. Again, so something squared, we just multiply the index by 2. Okay, and that's all over minus 4. Apart from the fact I forgot that was a minus sign, so that's a minus sign there. So that should be the minus sign. So well done, anyone who spotted that. So let's just get rid of that minus sign. This e to the 0, anything to a power 0 is just 1. So just rewriting that, we bring this to the front, get rid of cancel those minus signs, we get 2 minus e to the 2 I theta minus e to the minus 2 I theta. Okay, all over 4. Okay, so you can rewrite this as take out a factor of 2 here. We get a half into that'll just be 1, and then we get minus e to the I2 theta plus e to the I2 theta all over 2. Okay, so those two expressions are equal, but now we just identify that as being cos theta. So that's equal to a half 1 minus cos 2 theta, because it's just the cos theta, but we've got 2 theta instead of theta. So that's equal to the right-hand side. It was exactly what we had to prove, so we get a big tick there. Okay, so again, let's just run through what I did. Started with the left-hand side, rewrote it in terms of exponentials, expanded out the exponentials, remembering to get the signs correct. Don't forget your signs, that's where a big part of the problems arise, standard mistakes. So even me doing it in front of the board, just be wary of that when you come to check your answer. So I just expanded it out, rearranged it, and then spotted that those clumped those two terms together and noticed that those became a cos. And then we found exactly what we had to find out. Okay, so that's the first example. Okay, so let's put another example here. This time let's have something with a cos in it. So we're going to have cos cubed theta is equal to a quarter cos 3 theta plus 3 cos theta. Okay, so exercise is to prove this using the exponential forms of cos and sine. Again, these are the exponential forms. So what do we do? Again, exactly the same technique. So the left-hand side, in this case, is cos cubed theta, and we just write that down in terms of the exponential form. So this is e to the I theta plus e to the minus I theta all over 2 to the power 3. So we just expand that out, so we can use the binomial theorem here. So, well, on the bottom we just have 8, that's 2 to the 3, that's 8. On the top we have e to the I theta cubed plus 3 e to the I theta squared times e to the minus I theta plus 3 e to the I theta e to the minus I theta squared plus e to the minus I theta all cubed. So that's using the binomial theorem, or you can multiply it out separately if you prefer, but it's usually quicker to use the binomial theorem. So let's just rewrite these using the rules for indices. So let's just take out a factor of 8, save us a bit of space here. So e to the I theta all cubed, that's the same as e to the I 3 theta plus 3. So this is going to give us e to the I times 2 theta, but then we're timesing it by e to the minus I theta. So we need to add those together. So I2 theta minus I theta just gives us an I theta. So that's plus 3 e to the I theta plus 3. Again, e to the I theta times e to the minus I times 2 theta. We're squaring, so we can just bring that 2 inside. So that gives us I theta minus 2I theta. That gives us e to the minus I theta. And the last one plus e to the minus 3I theta, or I times 3 theta, I guess, if I'm being consistent. So now you should be able to recognise that if we collect these two terms together, I'm going to get something that looks like a cos of 3 theta. So I'll get e to the I 3 theta plus e to the minus I 3 theta, and we can take that with a factor of 2. So this is, let's just rewrite this. So this is a quarter into e to the I theta, I 3 theta plus e to the minus I 3 theta. So that's the term here and the term here, all over 2. I've just taken a factor of 2 from the quarter inside, plus 3 into e to the I theta plus e to the minus I theta, all over 2, to give me the second term. Okay, so just those two terms give me that, and I'm left with exactly the thing I'm supposed to have, so that's exactly equal to the right hand side, because that's just cos 3 theta, and that's just cos of theta. Okay, so as I say, this is just such a standard technique. You should remember to apply that when you're asked to prove formulae, whether or not it asks you to use the exponential form. You should just remember that this is a standard way to do it.